Sophia
I'll tell you
currently asleep, by the way.
It's 9:06.
Sophia here eventually.
So with you all, I recorded a shorter video. It was like only 42 minutes. And I'm gonna kind of rehash some of the stuff, at least the split exact sequences stuff. I went through, if you looked at the video, I went through the snake lemma in a very kind of hand wavy, crappy way. I wanted to give an idea of why that snaky part was actually well defined, which I think I did all right on that. But then I said, nobody wants to prove this morphism, blah, blah, blah. So there's more details in there, but I think I hopefully gave the idea there. I like this theorem. This is about the split exact sequences. Let be a short exact sequence of our model, the morphisms. The following are equivalent. Well, I'm gonna talk about this in more detail here. Well, all right, so oh, so good. Number one, there exists, let's call it H from C to D, such that when you do H and then G, you've got C. Okay. Yeah. Is isomorphic to conclusion of A, projection on C. So to be explicit here, and pi C, A comma C, C. So these conditions are all equivalent, and such a sequence that satisfies this satisfying one and all of these conditions is called a split exact sequence. Let me add to the joy here by pointing out that what do I mean to be isomorphic to this? So my meaning here is GF inclusion A, C, the identity of C, the identity of A, and so what I mean for this to be isomorphic is this original exact sequence can be put into this diagram, where this diagram is commutative, and this middle thing, this middle vertical drop is a isomorphism. So going here, the same thing, going here, the same thing. let me point out, one potential hazard for this. One potential hazard in this is the following. If you have a split exact sequence, that is to say, if the sequence splits, that means that B is the direct sum of the bookends. The converse is not necessarily true. So you might have a short exact sequence where this is the direct sum of the bookends, but it doesn't split. You really need these splitting matters to work in the opposite direction. Essentially what it means for this to be a split exact sequence is you can put it in reverse gear and run it the other way, but just like you can this here. Because notice, this is sort of symmetric in the sense that I could have gone inclusion into C, projection on that. Okay, so let's kind of go over some of this in a bit. Proof. I do love this, and I think it's a whole fun to do this a little bit. One implies two. So here's what we have. This is exact. And I have, yeah, I love that. I've got the H. Now somehow, I need to get the other splitting, if you will. Sometimes these maps are called splitting when it composes to the identity. Here we have, I need to build from here to here, right? So how do I do this? Well, I need to find an intelligent way, take some B in here and have it give me something here, right? But I mean, look, this is a one-to-one map. I would expect B to be much bigger in a certain sense than A. So how in the world do I do this? Yes,
You run it through GH.
that's right. Are you in the mafia? Right? It sounds like you're laundering money. That's what I'm gonna do. I'm gonna launder this thing. Alright. I'm gonna take this to G of B and then back here. So I'm gonna kind of run it through the washing machine, clean it. He goes GB and then back here. Right? Now, what do I know about what do I know about this element? Well, I know it's in B, but there's something even more special about it. And what's that?
It's in the kernel. So G.
It's in the kernel. In fact, well, this is true. Also, B minus HGB is in the kernel of G. Because when I apply G to this, this is GB minus GHGB. But the GH part is the identity function, right? So this is GB minus GB, which is 0. And the key here is, of course, the kernel of G is the image of F. Right, okay with that? And so what am I gonna do here? Well, I'm gonna let, K B be F inverse of B minus H G B. Where here, I'm going to use that, I mean like a pre-image here, right? So think of this, don't think of this as the inverse function, think of this as, is like actually a set, the pre-image. Now, the first thing, alarm bell goes off. What's the first thing I gotta worry about if I'm going to assign to B the pre-image of that more complicated element? Well, I guess I need to worry. I don't want F inverse to be the empty set, because then I've got a problem, right? Because I've got to assign B somewhere, I can't be empty. But it's not the empty set, because that remark over there, that thing's in the kernel of G, so it's in the image of F. The next thing I have to worry about is what's the cardinality of the set? This isn't a function if I've assigned B to like 2, 7, or infinitely many points, right? But F is 1 to 1, so this is a unique element, right? So this is for sure a function, because the pre-image of this is precisely a set of element. Yes,
It's gonna be function only on the image of F, right? Like F inverse is only a function on the image of F.
no, it's a function everywhere, because your input is B, and then you do this thing is now in the image of F.
Oh,
So you take your B, and you get the corresponding image of that, and that's the
Right.
problem that we solve.
right.
Okay, I guess I need to worry about this being a homomorphism, right? So let me point out that, note first that if A is in A, then if I do, so here I have my function K, it goes from B to A as promised. What is KFA? Well, this is K, or this is actually F inverse of, replace every B with F of A minus H G F of A. Right? Everybody okay so far? But notice GF is the zero map, right? Because that's doing F and doing G, right? So this piece is gone. And I get F inverse of F of A, which is A. So KF is the identity on A as promised.
How is it the zero map then?
Oh, it's from the exactness of this, because when I push this twice, when I go F then G, then it's gotta be zero, because the image of this is the kernel of X.
Oh, okay.
Dr. Broden, how does H of 0? It's not just like a H isn't like just taking the pre-image, right? Because otherwise it'd be the kernel.
H is a homomorphism, so when I put in zero, I'm gonna
Right,
get
okay.
zero. Right. Everybody okay with that? I guess really, I should probably pay attention to the fact that this is a homomorphism. So the function is well defined, it does what we want as far as the composition being the identity. What about homomorphism? Well, then K this is F inverse B plus B prime minus HG B plus B prime. Right? And this is F inverse B minus HG. Here I'll literally use the fact that both G and H are homomorphisms, so their composition is a homomorphism. Everybody cool with that? Not too fast and loose for you? Now, notice that, so let me take an aside here. Suppose F of A equals B. Why I have a prime here, I'm sure I don't know, so that's what it's supposed to be there. Suppose F of A is this animal, and F of A prime is this animal. I know that such an A and an A prime exists because, again, by our arguments before, this is in the kernel of G, so it's in the image of F. Everybody okay with that? This means that A plus A prime, well, notice that B minus HGB plus B prime minus HGB prime. Right? Because of the fact that F is a homomorphism, this should be F of A plus F of A prime. And this is also equal to okay, so let's get this kind of organized here. So what does this mean? This means that A plus A prime is equal to F inverse H H right. Which is this thing, K of B plus 1. And K of B plus K of B prime is equal to F inverse of HGB plus F inverse B prime minus HG. And this, of course, is equal to whoops, this is actually equal to A plus A prime. That's equal to A and that's equal to A. Therefore, K of B plus B prime is equal to K of B plus K of B prime. So that shows it's an abelian homomorphism. See if you can prove that the R factors out, that the scalar multiplication does. That's actually easier. Okay, any questions on that? All right, so there's 1 implies 2. How about 2 implies 3? Two implies 3. For this one, we now have the splitting on the front end. And now when you do F and then you do K, you're the identity on A. Now, with this, I want to show that this is isomorphic to the sequence here. So I need to show so really the important thing in showing those two sequences are isomorphic is finding this phi that goes from B in that direct sum. So I'm going to define phi or B okay, folks, help me out here. Take a look at my diagram. What is this gotta be? Right? What's the easiest thing to do? Because we're going to be lazy people. Given an input B, I need to associate an ordered pair. The first coordinate A, second coordinate in C. Right, let's give it a shot, shall we? Use my K tool to get the A and use my G to get the B. Or to G to get us the element C. Right? Okay, this is more easy than the other one as far as, well, does everybody give me the fact that this is a homomorphism? Because you've got a homomorphism in both coordinates, right? So this is an R module homomorphism. The real question is this an isomorphism? So let's check out 1-to-1 first. Let B be in the kernel of phi. This means K of B, G of B is equal to 0, 0. So what can we deduce from this? I don't know much about K except it splits F, but since G of B is 0, what does that tell me? That B is in the kernel of G, right? And because of the exactness of the original sequence, the kernel of G is equal to the image of F. So there exists A and A such that B is equal to F of A. Now, take this and compose it with K. K of B is K F of A, which is A, but K of B is 0 because that first coordinate is also 0. Therefore, A equals 0 And so B, which is f of A, is also 0. Therefore, phi is 1 to 1. Okay. That wasn't too bad. Fine. How about on to? This one's it's a little bit more thorny. So let me kind of scribble here. What tools do I have? So let's just kind of play with this for a minute and see if we can come up with anything intelligent here. I've got this splitting back. Now, I want to be onto, right? So if I give an arbitrary element here and here, I need, there exists a question mark B such that B of B equals A and C. Right? So we've got to find a way to take a B and when it goes this way, get the C, go this way, get A. Now going this way to get the C is not too difficult because this was onto, right? So an obvious choice is there exists B and B such that G of B is equal to C. But there's no real guarantees that when I do the K of B, I'm going to get A, right? And that's the real problem. I mean, so what? I mean, here's what I get. So I get K of B, C, and you know, who knows? Right? Now, the one saving grace in my preparation for Harakiri here, because this looks awful. The one thing that I know is certainly I do not expect this B that I chose to be unique. Right? There may be many choices, and maybe I made a bad one. How do I even know what choice I made? How can I adjust this? Fix it. Well, I can adjust B. Adjust B by any element in kernel. Right? I could stick on, so notice if G of B is equal to C and X is in the kernel of G, then G of B plus X is G of B plus G of X, which is. So in other words, I've got a lot of freedom. I can adjust this by something in the kernel of X, which actually is the image of. So any ideas what I might do? Well, notice one thing. Remember, I want to get an A in this first coordinate, right? Everybody agree with that? Notice that f of A is in the image, so it's in the kernel. Right? And remember what I'm doing to B, to go back to A, is I'm doing K to it. So this suggests that I'm going to do something like this. Is this gonna Well, what happens if I put B plus F of A into this? When I do G, I'm gonna get C, which is what I want. When I do K, I'm gonna do the KF of A is looking good because that just gives me A. But now I've got that G, now I've got that KB. And I don't, yeah, right? Watch this. How about this? Let's clean it again. This is what I want. I'll certainly,
Dr. Boyd,
oh, yes,
we didn't show that H exists.
what?
We didn't show that two implies one, so we don't know H exists.
Yeah, that's right. I don't want that anyway. So I'm gonna clean it another way. Let's go, that's exactly what I want to do. Let's look at B. I think this is what I want to do. Let's go K. Yeah. That's in B, that's in B, KB, yes, that's what I'm, let's do this. Notice this is in B. Because F and KF is in B as well. So if you look at G of B plus FA minus FKB, this is GB plus GFA minus GFKB. Oh yeah, that's right. This is C. FG composed is 0 because of the exactness of the original C. And here's another GF, which is 0, so that's gone. So I get C. So in particular, this chunk here is in the kernel, right? Of course, it has to be because it's in the image path. On the other hand, if you look at K, this is KB plus KFA minus KFKB. This is KB, nothing I can do about that. When I do F and K, that's A, because KF is the identity. And again, with the KF, that's the identity. And look how lucky I am. KB's cancel, I get A. So there is the image, this is the thing that goes to A comma C. Okay. So we got this. The last thing we have to do is 3. Oh, no, let me not get carried away here. Let me just kind of, there is one thing I want to make sure that you all are on the page with the fact that these are isomorphic. So here's what we have so far. 0, A, B, C, 0, 0, A direct sum C, 0, identity C, identity A, and I'm gonna call this phi. This is the thing that we just built. Right? This is the identity on A, this is projection on C. This is exact, this is exact. All we really need to do is show the diagram use. So let me kind of talk you through that. What happens when I go here? I go to F of A. And then what does phi do? Well, phi takes this to KFA and GFA. And KF is the identity. And GF is 0, so this is just A0. So that's the same thing we get going in the other direction. Right? So this part of the square commutes, because when I go here, I go to A, because it's the identity, and this goes to A comma 0, which is where this one, right? Let me check the other square. If you start here with B, this goes to G of B, and this goes to G of B, because that's just the identity. Going here, this goes to KB, GB, and that's where this goes, because this is projection on the second coordinate. So the diagrams commute, and so it's us. Okay with that? Any questions? The last one that we're gonna get is not so hard, I don't think. We're gonna show 3 implies 1. So we have the following commutative diagram. So we have this following commutative diagram, and basically I have to build the splitting, right? Find H from C to B such that find an R module homomorphism C to B such that that composition is the identity on C. So this is like really more detailed. I need start with a C up here. How am I supposed to get here? Just walk, in the words of Stephen Tyler, walk this way, right here. Take C, do the identity on C, which just, this is kind of a silly step. I'm just putting it down in this box. Now, I am going to project, I'm going to do the inclusion into C. Right, so that would take that to 0 comma C, right? So it's the analog here. This is the cool thing about running it in reverse, and then I'm going to do phi inverse. And phi inverse makes good, clean, wholesome, all-American sense because it's phi is an isomorphism, right? Now, this is an R module homomorphism. Because all these are, so no problem there. We need to show really that it composes the way we said it does. So let C be in C, then G H of C is G phi inverse, inclusion C, identity C of C. Now let's just hope we can see out of this. Let's see what happens. Identity of C, identity on C of C is just C. This is G of phi inverse of 0, oops, yes, 0 C. And what is this then? Right, remember phi inverse This is phi inverse. And phi of B equals K of B, G of B. So, to ask yourself what's phi inverse, ask yourself, where did 0, comma C come from, right?
Dr. Rosenbaum, can't you just skip that because you know G of P inverse is gonna be C?
Oh, yeah. Yeah, well, we can, that's actually a good idea. So we know G, well, actually, that's kind of a good way to do it. We also know by the commutativity of the diagram, G and the identity of C is equal to P, and so that is to say, G is equal to pi C B. Agreed? Therefore, yeah, so we don't have to work back through the math. Therefore, phi inverse of G is equal to pi C. Oops, too much commutative algebra for me. G phi inverse is pi C. Goes on that side. There we go. So up here, this is equal to there you go. Okay, any questions on that? Any questions? All right. What we want to talk about now, give kind of a little introduction to it, if you will. We're going to start, and I gave you kind of a little teaser in the homework this week, kind of a simple case to build up to it. We're going to talk about 3 R modules. Free modules are, in a certain sense, the best. So R modules, one of the things that I said is they generalize vector spaces, right? A module is to a vector space as a ring is to a field, right? Fields have very boring ring structure from what everything is either 0 or a unit. And that makes their modules behave very nicely. Even with a pretty nice ring like Z, we see that there are modules that are strange, the kind of things you would expect to find in vector spaces like Z2 or Q. These are all Z modules. A free module is a best approximation. If I fix a ring R, and my rings will have identities unless specifically mentioned otherwise. If I fix a ring R, a free module is the best approximation to a vector space over R. And what's one of the big things about vector spaces from day one is vector spaces had a basis, right? And the basis was cool because even though the vector space has lots and lots of vectors in it, when you did linear algebra, something like 3110, if you're looking at R2, all you need is this basis. Every basis is a linear combination of the vectors 1, 0, and 0, 1, right? Any linear transformation, if you want to know how that linear transformation is working, all you have to do is see how it affects your two basis vectors, and that tells you how the whole dang thing's working, right? Which is kind of cool. In our modules, we have something similar. They're not quite as good, but they're close. We'll examine the connections and the things that don't line up so well. what's the first thing about a basis? A basis was a generating set. They didn't call it that linear algebra. Oh, it spans it. It's a generating set that is as efficient as possible. And that efficiency was termed in terms of what we call linearly independent. Right? So the first thing we're going to do is let's talk about what it means for a set to be linearly independent. Definition. Let let's say M be an R module. And
This is the empty, right?
yeah, I don't want this to be empty here. We say X a subset. I'm going to make it clear. X is just some non-empty subset. Say X is linearly independent if given any X1, X2, X distinct, don't it? Didn't say that one else, so I should have. Given any distinct in X, the relation R1 X1 plus R2 X2 plus R in Xn is equal to 0 implies Ri equals 0. So this is, I think, what you might think it is. This is the notion of linear independence from linear algebra, right? So it's a linearly independent set of elements of the module if given any finite sum of this form. If that finite sum is 0, then all the coefficients, all the RIs have to be 0. Right? Notice, of course, that X could be an infinite set, but you only consider finitely many of these at a time. A free module is going to be the ones that actually have a basis, right? And we're going to talk about that. I'm going to give you several and actually free modules again are a solution to a universal mapping problem as well, just like direct sum and direct product. Yes.
This would change if the ring we're working in wasn't an integral domain, or sorry, wasn't an integral. No.
Yeah.
So even if we have 0 divisors,
Even if you have 0 divisors, the definition of linear independence is the same.
Okay.
So for example, if you look at Z6
sure,
as a Z module, there is no linearly independent subset. Because even a single element subset, if you multiply it by 6, you get 0.
Right.
However, as a Z6 module, Z6 does have a linearly independent subset, namely 1. Because to multiply something from Z6 and get 0, it has to be 6, which is 0, right? So, okay, other questions? Okay, we will see you all next.